Okay, so let's dive into a competition. It starts out sounding simple, but it quickly spirals into the absolute limits of what we can prove and maybe even what we can know.
So, picture this. We're playing a game. The rules are super easy. Write the longest-running computer program you possibly can, but you can only use a tiny, fixed number of instructions. Sounds like a neat little puzzle, right? But as you're about to see, the answers get really strange, really fast.
This one simple question is what kicks off this whole journey, and it seems so innocent. But the answer? Well, it's bigger and, honestly, way more mind-blowing than you can possibly imagine.
All right, so for a program with just one state, and you can think of a state as just a single instruction, the longest it can possibly run is one step. Easy. For 2 states, it's 6 steps. For 3, it's 21. Okay, it's growing, but the numbers are small. Seems totally manageable. For now.
Now, when we get to a 4-state program, the record holder jumps up to 107 steps. It's a bigger leap for sure, but it's still a number we can wrap our heads around. You can write it down, no problem. Nothing to see here. Yet.
And this is where everything changes. For a 5-state program, the champion runs for over 47 times million steps. Yeah, that's not a gradual increase. That's an explosion. We've gone from a gentle slope to a rocket launch, straight up.
Just when you think it can't get any crazier, it does. The 6-state champion runs for a number of steps so large it has over 36,000 digits. I mean, let's put that into perspective. The number of atoms in the entire known universe has about 80 digits. This number isn't just big, it's living in a completely different reality.
So this whole competition has a name. It's called the Busy Beaver game, and the function that describes these ridiculously huge runtimes is the Busy Beaver function, or BB of n. It was dreamed up by a computer science pioneer named Tibor Rado back in '62, basically as a way to poke at the absolute limits of computation.
So what's one of these things actually doing? Well, here's a simple 2-state machine in action. You can see it just moves along this tape of zeros, flipping them to ones based on its simple rules. It zips back and forth for a bit, and then, bam! After exactly 6 steps, it hits a halt instruction, and it's done. This tiny program is the undisputed champion for n equals 2, and that's how we know BB of 2 is exactly 6.
So now for the big question. Why does this happen? Why do these numbers grow so fast that they just break our brains? The answer reveals one of the deepest truths in all of computer science.
The reason for this completely insane growth is that the Busy Beaver function isn't just big, it's what's known as uncomputable. And that means there is no single computer program that you could ever write that can calculate BB of n for any number n you give it. It literally grows faster than any function we could possibly program.
This whole thing is directly connected to one of the most fundamental limits of computing, the halting problem. All the way back in 1936, Alan Turing proved that it is impossible to write one program that can look at any other program and tell you for sure if it will eventually stop or just get stuck in an infinite loop forever. And here is the crucial link, the key to the whole thing. The Busy Beaver function is like a cheat code for this impossible problem. If you had some magic machine that could just tell you the value of BB of n for a program with n states, you could solve the halting problem. You would just run that program for that exact number of steps. If it hasn't stopped by then, you know for a fact it's going to run forever. Why? Because the Busy Beaver number is the absolute maximum number of steps a halting program of that size can possibly run.
Now, what's so fascinating is that this very modern idea of uncomputability has this secret connection to a problem from pure mathematics that's over a century old.
Okay, so let's travel back to the year 1900. The legendary mathematician David Hilbert lays out 23 huge challenges for the future of mathematics. His 10th problem sounds simple enough. He just wanted someone to find a universal method to tell if any given polynomial equation has a solution using only whole numbers.
And you can see how this works in some cases. It's easy. The equation on the left, yep, you can find whole numbers to plug in that make it work. The one on the right? Nope, impossible. You can't square 2 integers, add 1, and get 0. Hilbert wanted a single process, a single recipe, that could give you a thumbs up or thumbs down for any equation you could dream up.
So for 70 years, some of the smartest people on the planet worked on this problem. They weren't looking for a solution to every equation, just for that one universal process. But the final answer was a total shock, because it didn't come from number theory. It came from the world of computation.
It took decades of work by 4 brilliant minds: Davis, Robinson, Putnam, and then finally Yuri Matiasevich in 1970.
And the answer they found was a definitive, resounding no. Such a universal method is impossible. It simply cannot exist.
And this right here is the core insight. The reason it's impossible is because these simple-looking equations, they're like a secret programming language. They're so incredibly powerful that you can actually encode any computational process, any algorithm at all, as a question about whether a specific equation has a whole number solution.
So, finding a universal method to solve all these equations, it turned out to be the exact same impossible task as solving the halting problem. They're just two different languages describing the same fundamental, uncomputable limit. They are two sides of the very same coin.
This deep connection doesn't just link two different fields. It takes us right to the ultimate boundary of mathematics, to a place where concrete numbers can represent truths that we can never formally prove. Just think about this for a second. We can design a Turing machine, a 27-state one, let's say, that does nothing but search for a counterexample to a famous unsolved problem, like the Goldbach conjecture. It's programmed to run forever unless it finds one. If it finds one, it stops. So if we knew the value of BB of 27, we could just run our little machine for that many steps. If it's still running, we would have just proven the conjecture's true.
We can take this even further. I mean, way further. It's possible to design a 748-state Turing machine that methodically searches for any logical contradiction inside our entire standard framework of mathematics. This machine is built to do one thing: halt if and only if math itself is broken.
But here comes the final, absolutely mind-bending twist. Kurt Gödel's famous incompleteness theorem says that no consistent system of mathematics can ever prove its own consistency. That means we can never prove that our 748-state machine runs forever. And if we can't prove it runs forever, we can never be certain that we found the longest-running program of that size. We can never, ever know the true value of BB of 748. This puts a hard, definite limit on what we can know. The number BB of 748 is a real, specific integer. It exists, but its exact value is fundamentally unknowable. It represents a truth that is forever beyond the reach of human proof. And that just leaves you wondering, what other truths are out there, waiting just beyond the edge of knowledge?